Hi everyone, this is part 2 of polyprotic acids and bases. This is going to be the last video for this chapter. Let's get started. We resume this video with the intermediate form of a polyprotic acid. Unfortunately, a solution prepared from an intermediate form is more complicated. Actually, it's a lot more complicated because it's both an acid and a base. A molecule that can donate and accept a proton, so it can do both things, is called amphiprotic. So leucine, which is the amino acid and which also is the intermediate form of this polyprotic acid, is considered amphiprotic. So let's take a look at the two different reactions that it can do. If it's going to donate a proton, it'll be the first reaction, which is HL dissociates into H plus and L minus, and there's your Ka with 1.80 times 10 to the negative 10. Now, if it did the other thing, if it accepted a proton, then it would do the second reaction, and there is the Kb. Since the acid dissociation reaction has a larger value, then we expect leucine itself to be acidic. However, just because we say that it's, we think it's going to be acidic, it doesn't mean that we can simply ignore the base hydrolysis reaction. Ka is larger, but both reactions proceed to a nearly equal extent. I mean, one's 10 to the negative 10, one's 10 to the negative 12. Because the H plus that's produced in the first reaction is going to react with the OH that's produced in the second reaction. And therefore, that's going to drive the reaction to the right, making Ka and Kb nearly equal. To treat something like this, I'm going to go ahead and talk through, this is all in your book, but I'm going to go ahead and talk through how they determine or how they treat a case like this, a case where you have an amphiprotic type molecule. You are not responsible for deriving the expression at the end of this talk, but it's good to know how they got it. So to treat a case like this, you have to write the charge balance. Charge balance is not discussed really in this chapter, but all it says is that the sum of the positive charges in the solution must equal the sum of the negative charges. So the problem originally from our last video said that we had 0.0500 molar leucine, in which both of the reactions can happen, this Ka and the Kb. So what's the charge balance? Charge balance of the positive side would be the H2L plus and the H plus. So those are the two positive charges that we have. Well, what's the negative charges? It's going to be L minus and your OH minus of your Ka and your Kb. From that acid dissociation equilibria, we can replace H2L with what H2L actually equals, which ends up being HL times H over K1. And then we do the same thing for the other side, for L minus. We substitute what L minus really is, and it's K2 times HL divided by H plus. And then at the same time, we can always write what OH equals, which is KW over H plus. The next thing you do is you solve for H plus. To do that, you've got to multiply all the terms by H plus, then you have to factor out H plus squared and rearrange a bunch of variables. If you multiply the numerator and the denominator by K1 and take the square root of both sides, that gives you your H plus. Then you have to make the assumption that since HL is the major species, and you know that neither the first reaction or the second reaction go very far because it's a weak acid and a weak base, the concentration of HL in that equation that you have will be 0.0500. So you replace the HL concentration with your formal concentration. And then another assumption you do is that the first term in the numerator is always going to be greater than the second term, because if you follow your book, the first term has K1 and K2 multiplied by each other, and the second term only has K1. So it's going to be much greater. So the second term, they drop it, and they also drop the first term in the denominator. That ends up canceling F in the numerator and the denominator, and then you make use of your log identities, all to get to the final expression, which is this. The pH of the intermediate form of a diprotic acid, so intermediate form being like HL, like leucine, an amphiprotic species, is approximately midway between pK1 and pK2. So for leucine, gives a pH of 1/2 times the sum of pK1, which was 2.328, that's from the table, plus the pK2, which is 9.744. It equals 6.036. And of course, that'll tell you that the H plus concentration of leucine is 9.20 times 10 to the negative 7th molar. Like I said, you don't have to know how I derived this expression, but it is a good exercise for you to go through it in the book step by step and make sure that you understand it. The more you practice it, the more you understand why it is that this is the expression that they ended up with. So once you have that, because you have this awesome expression that we just made, you can actually find the concentrations in the solution of leucine, of 0.0500 molar leucine. You can find the concentrations of the other guys, H2L plus and L minus, just by solving the K1 and K2 expressions. The original reactions of the diprotic acid said that H2L plus associates into HL and H plus, and that's your K1. So if you solved for H2L plus, you would get HL times H plus is over K1, and you use 0.0500 as the concentration of HL, which is the formal concentration of that solution. So it would be 9.20 times 10 to the negative 7, which you just found for H plus, times 0.0500 divided by your K1, which was 4.7 times 10 to the negative 3. And that gives you a concentration of H2L plus of 9.79 times 10 to the negative 6. You can do the same thing for the concentration of L minus by using the original reaction of the diprotic acid. HL dissociated into L minus plus H plus, so the equilibrium expression would be K2 is equal to L minus times H plus over HL. If we solve for L minus, then you would get K2 times HL over H plus, of course using 0.0500 again for the concentration of HL, using the K2 that you know for leucine, and using what you calculated for H plus, 9.20 times 10 to the negative 7, multiply and divide all that out, you'll get 9.78 times 10 to the negative 6 molar for concentration of L minus. So that's how you deal with the intermediate form of an amphiprotic molecule. Again, you're not required to know how to derive the pH is equal to 1/2 times pK1 plus pK2, but I suggest you do go through the book and understand it and do a couple more problems like this. All right, the last thing I want to talk about in this video and in this chapter is which is the principal species. Sometimes we need to identify which species of acid, base, or intermediate form is predominant under a certain condition. For example, if I told you that the pH of benzoic acid was 8, what is the principal form of benzoic acid? Is it benzoic acid or is it benzoate, which is the anion of that? And remember, the pH is 8 because it just happens to be 8. I mean, the pH is a result of everything in the solution. It could be that, you added some NaOH, so it made it 8, or you added a phosphate buffer. I mean, it doesn't matter how it got to 8, it just happens to be 8. So we have to find out what is the principal species in this solution. The pKa, they give you the pKa. The pKa for benzoic acid is 4.20. Therefore, what does that mean? When the pH is 4.20, that means that there's a 1-to-1 mixture of the weak acid to the weak base conjugate. Because remember, at pH equals pKa, that means that ratio A minus to HA is 1. So if the pKa is 4.20, then at pH 4.20, there must be a 1-to-1 mixture of the weak base and weak acid conjugate. What would be the ratio at pKa plus 1? So if the pH is 4.20, what about if I did, pKa plus 1? So that means that the ratio of A minus to HA would now be 10-to-1. And you can solve this mathematically. If you set pH to equal pKa plus 1, and you have your other side of your equation, which is also pKa plus the log of A minus to HA, your pKa variable cancels, and you get 1 is equal to the log of A minus over HA. If you solve for that by raising 10 to the power on each side of the equation, you'll see that you get 10. So the ratio is 10 to 1. So think about it. If you did it for pK plus 1, what would be pK plus 2? The ratio would be 100 to 1. And that would be, of course, a pK of 6.20. The Henderson-Hasselbalch equation, you can substitute 8, that pH, right? That's the pH. So substitute 8 for pH is equal to the pKa, which is 4.20, and then just solve. And you'll see that 8 minus 4.20 equals 3.8. 3.8 is equal to the log of A minus over HA. You raise 10 to the power on each side, and you'll see that there's almost 10,000 times as much A minus as HA. So the principal species at pH 8 would be A minus, which is the conjugate base form of benzoic acid, which is the benzoate ion. So what's the point of this? The point is that for monoprotic systems, the basic species A minus is going to be predominant when pH is greater than pKa. The pH that they gave you was 8 for benzoic acid, and it was greater than the pKa, which was 4.20. So that means that the benzoate ion, or the A minus form, is going to be predominant. Obviously, the opposite is also true. When pH is less than the pKa, so let's say that I gave you a pH of 2, and the benzoic acid had a pKa of 4.20, then the HA, the benzoic form, is going to be predominant. So this little graph here is useful for you when you're trying to figure out what's the principal species in a certain solution at a certain pH. Let's try one. Principal species, which one and how much? What is the predominant form of ammonia in a solution at pH 7.0? So the first thing you have to do is go to the back of the book and figure out, okay, ammonia. And of course it would be in the form of ammonium ion. Then you'll see that the pKa is 9.24. So right here they give you a 7 pH. So that means that the pH is lower than the pKa, which means, according to our little graph, that the HA form, or the acidic form, is going to predominate. So the NH4 plus species is going to predominate in this solution at a pH of 7. Second part of this question is approximately what fraction is in this form? Well, the pKa is 9 or 9.24 and the pH is 7.0. So it's a pKa minus 2, so that's a 100 to 1 difference. Or I'm sorry, 1 to 100 difference, because the NH4 plus is on the bottom of the fraction. So about 1 to 100 is the amount that's going to be in NH4 plus form. So what about diprotic systems? Well, the reasoning is similar. The only thing is that there's 2 pKa values. So, for example, if I gave you fumaric acid, which that's the H2A form, and the fumaric acid has a pK1 of 3.02 and a pK2 of 4.48, at the pK1 you have your H2A form and the HA minus form at 1 to 1, and at the pKa2 you have the HA minus form and the A2 minus form at a 1 to 1 ratio. And this little graph right here shows you the major species in each pH region. So at pH values below pK1, then the H2A is going to predominate. At pH values in between pK1 and pK2, then the HA minus is going to predominate, and obviously the A2 minus is going to predominate at pK2 values and above. And of course, we can't leave out triprotic systems. So this is the chart that you would use for if you have trying to figure out what's the predominant species in a triprotic system. Realizing that, of course, there's, instead of 2 pKa's now, there's 3 pK values. So you can just figure out if you have your pH at less than the pK1 value, then obviously the H3A form is going to predominate. And you have the H2A and the HA2 minus form, which show that the pH of the first intermediate species, H2A minus, is the 1/2 pK1 plus pK2. At that pH, the concentration of H3A and HA2 minus are equal. And the same reasoning goes for the HA2 minus region. So that is it for this video. Please study hard, and I will see you later. Bye-bye.